So, in this session we are going to discuss about the combination of ideal reactors, like what will happen if Cstr individually they are combined or connected in series, or PFR connected in series, Cstr Pfr mixed combination, series parallel combination, etc. So, to start with, so this is a combination of ideal reactors, right. Generally you see that first we will discuss combination of PFRs, right. So, first one, series combination. So, what will happen if I connect n numbers of PFRs in series? Here it is Fa naught, Xa naught we will consider to be 0, V naught and Ca naught. Say this is I equal to 1, here we will have Xa1, Ca1. So, this is ith reactor, Xai minus 1, Cai minus 1, here we will have Xai, Cai, this is the nth reactor, Xan minus 1, Can minus 1, and finally Xan and Can. Now, see, for this ith reactor, if I write the design equation, Vi by Fa naught, remember this is not Fai minus 1, it should be Fa naught. Why? Tau I by Ca naught, here we will write the conversion from Xai minus 1 to Xai dxa by minus Ra, right, because the lower limit actually accounts for this initial conversion. Okay. So, that is why this Fa naught or Ca naught, whatever we are choosing, must be the concentration of unconverted stream. So, these are of unconverted streams or stream. Now, for n reactors, if you go on adding, I will get summation of Vi by Fa naught, which is V total by Fa naught, equal to summation I equal to 1 to n Xai minus 1 to Xai dxa by minus Ra, and this will eventually give 0 to Xan dxa by minus Ra. So, the series combination and a single PFR of large volume, they are actually identical. So, this is same as a single PFR of volume Vt is equal to sum of Vi, right. So, you are not getting any specific advantages when we connect PFRs in series. So, our conclusion or inference is, as we are not getting any specific advantage over or upon connecting PFRs in series, we always use a single PFR instead of combining them or instead of connecting them together. Right, definitely this connection is following the series combination. Now in parallel combination, what will happen? Say we have one I and N. Right. So, we must have here same conversion at the outlet, that is say XAF, right, because if we have different conversion they will be mixing up and again it may create a problem. So, if this is FA naught and here it is FA naught 1, then FA naught I, then FA naught N. So, definitely FA naught will be equal to FA naught 1, FA naught 2, FA naught N. Right, that is obvious from this balance at the point. And if I want to have same combination for ith reactor, we have Vi by Fa naught I equal to 0 to XAF dXA by minus Ra. So, we need to note that this part should remain constant for all the different parallel branches. So, V1 by Fa naught 1, V2 by Fa naught 2, Vn by Fa naught n. Right. So, we are getting here n number of equations and from there we can solve n minus 1 here and actually this is 1. So, total n number of equations. So, this is 1, this is 2. So, from equations 1 and 2 we may solve for FAI. Okay. So, that is the this underlying kind of rationale behind using the PFRs in series, right. Now, if I have a series parallel combination of PFR, we are not going to discuss it separately. So, you see that if I have 5 or 6 PFRs in series, we can actually replace it by a single larger PFR and we can apply the same formula on this combined PFR in each of these parallel stream, right. Now, next we will think of Cstrs in series and we will see whether we are getting any advantage of relative to the case of a single largest CSTR. So, CSTRs in series. So, this is ith reactor, fast. So, here we have the Ca0, Xa0 equal to 0, Fa0, V0, right. And from there, it goes to ith, Vi, this is Ca1, Xa1, Ci minus 1, Xi minus 1, and this is the nth reactor, Can minus 1, Xan minus 1, producing Can, Xan. This is Vn. Right. So, for the ith reactor, we have tau I by Ca naught, again that of unconverted stream, is equal to Xai minus Xai minus 1 divided by minus Ra at Xai. So, that is the performance equation of this ith CSTR, and that can also be written as Vi divided by Fa naught. Right. Now, for constant volume reaction, we have tau I is equal to Ca naught into Xai minus Ca naught into Xi minus 1 divided by minus Ra at Xi. So, this will give you Ca naught minus Ca I minus Ca naught minus Ci minus 1 divided by minus Ra at Xi. So, this Ca naught cancels out, Ci minus 1 minus Ci divided by minus Ra at Xi is equal to tau I. Right. So, in this way we can proceed, and finally we can calculate the outlet conversion, but before that we want to show you that whether we can extract any advantage relative to a single CSTR of larger volume, which is sum of these Vi. Right. So, for that we will simplify the case. Let us further consider a first order reaction. Right. That is minus Ra equal to Kca. So, tau I is equal to Ci minus 1 minus Ci divided by Kci. So, K tau I Ci minus 1 minus Ci is equal to K tau I plus 1 Ci is equal to Ci minus 1. So, Ci minus 1 divided by Ci, 1 divided by 1 plus K tau I, correct. So, with that, let us go for writing the product of this Ci minus Ci divided Ci minus 1 divided by Ci. So, what you can write, Ca naught divided by Can is equal to Ca naught by Ca1 Ca1 by Ca2, Can minus 1 by Can, and that's equal to successive product of this, right? Let's also consider the Cstrs are of same size, that is tau 1 equal to tau 2 equal to tau I, or tau, all this tau are same. So Ca naught by Can is equal to 1 plus k tau to the power n. So that is Ca naught by Can whole to the power 1 by n minus 1 into 1 by k equal to tau. So the tau total, the total space time, n into tau, so n by k into Ca naught by Can to the power 1 by n minus 1, right? Now you see, we will show you that if I combine infinite number of Cstrs in series, it will be going to give you the Pfr, right? So for Pfr, the design equation for Pfr, the design equation is basically k into tau total is equal to minus of ln 1 minus xan or xa, right? So it is xa is equal to 1 minus e to the power k into tau total. So that's for Pfr. Now limit n tending to infinity for Cstrs, limit n tending to infinity, this tau total equal to what? This is equal to limit n tending to infinity 1 by k into 1 divided by 1 by n into Ca naught by Can to the power 1 by n minus 1. Okay. So you know that limit x tending to 0, a to the power x minus 1 divided by x equal to ln a. So tau t is equal to 1 by k ln of Ca naught by Can, Ca, not Can, it's equal to minus of 1 by k ln 1 minus xn. So obvious is that xn is equal to 1 minus e to the power k tau t, right, which is same as that of Cstr. So our conclusion is the infinite number of Cstrs for a positive order first order reaction is going to give us the same performance as that of a single Pfr, right. So the performance is improving because upon combining Cstrs in series, because we know that for positive ordered reaction the volume requirement of a Cstr is lower than that of Pfr. So theoretically, you see, here I have Ca0, here I have Can, right? So this is 0, this is tau 1, tau 2, tau 3, tau n. So what is happening? This. This is happening. Right. Now, if I go on, this is infinite. Right? If you go on using the smaller and smaller and smaller Cstrs, so actually, sorry, this will be like this. I have done a mistake here. So if we go for let me draw it afresh. This is the curve for PFR, right? So this is for n numbers of Cstr. For infinite number of Cstr, it will be like this, in this way, right? So this is the typical step-like change of concentration in a Cstr. So what we have proved that infinite number of Cstr is going to give us the performance of a single PFR, and PFR, as you all know, that it's having much superior performance than Cstr for positive ordered reaction. So what we can confirm that actually the performance of a Cstr is improving upon attaching them in series, right, a Cstr cascade. So though we have established the fact, and what is the fact? One PFR is equivalent to infinite numbers of Cstrs in series, right? Establish the fact for first order constant volume reactions, it is true or it is general for any other reactions, right? Graphically, we can also establish that multiple numbers of Cstr is always advantageous in series. Graphical proof that Cstrs in series is better than a single Cstr. Why? Because you see, if I have a positive ordered reaction 1 by minus Ra versus Xa, and this is my fixed outlet conversion, so the respective volume of the single Cstr what we need is proportional to this. So V by Fa naught of a single Cstr is proportional to this, right? Now if I am using two Cstrs in series, just two, say with an intermediate conversion Xa1, So this will be the total volume requirement. Right. So for this is for single Cstr. Now V1 by Fa naught plus V2 by Fa naught, 2 Cstrs will have this area. Which is lower than the only dotted area. Right. So this dotted area we are not having, we don't have to incorporate in this combined Cstr. So Cstrs in series are always recommended for n greater than 0, that is a positive order reaction relative to a single Cstr, right, because we have a volume saving. Now next, it's obvious that how to solve for this intermediate concentration XA1 if I am supplied with the volume of the Cstrs, like V1, V2, V3 are given, and we have to find out the intermediate concentration or conversion. So our point here is how to determine the intermediate conversion of Cstrs in series. So you see that here we can have different size. Volumes are given. So here it is Fa naught, Ca naught, V naught, Xa naught equal to 0. Now it goes to a second smaller one of volume V2 and finally going to this another larger one of volume V3. Right. So here it is Ca3, Xa3, this is Ca2, Xa2, and that is Ca1, Xa1. Now you see that how we can write for constant volume system. For constant volume system, tau I by Ca naught is equal to Xai minus 1 divided by minus Ra at Xai. So that's equal to, so tau I is equal to Ca naught minus Cai minus Ca naught minus Cai minus 1 divided by minus Ra at Cai. So this is Cai minus 1 minus Cai divided by minus Ra at Cai, which is tau I. Right. So what you can do, knowing Ca naught, we can solve for Ca1 if tau 1 is known, and we also know the reaction kinetics, that is minus Ra as a function of Ca. Right. So, sequentially, we can find Ca1, Ca2, Ca3, Can. So, that is the algebraic technique of finding what will be the successive concentration and conversion. But alternative to that, there is a graphical technique. Called Jones method. What is that? See, from here we can write 1 by tau I with a minus sign is Cai minus minus of Ra at Cai divided by Cai minus Cai minus 1. So, this minus 0. Okay. So, what is the method? Draw a profile of minus Ra versus Ca. Locate Ca naught on Ca axis. Draw a straight line from the point Ca naught comma 0 with a slope equal to minus of 1 by tau 1. Right. Drop the point of intersection between the line with slope equal to minus 1 by tau 1 and minus Ra versus Ca plot or Ca profile to Ca axis. According to the equation, this must be Ca1. Right, because here I equal to 1, so Ca0, so Ca0 you drop a slope of this, draw a line with a slope of minus of 1 by tau 1 and drop it on the Ca axis, you must get Ca1, right. So, repeat the same procedure for Ca1, Ca2, etc. So, what is the graphical interpretation? If I have minus Ra versus Ca, any arbitrary kinetics, right, you locate the point Ca0 and draw a straight line with a slope equal to minus of 1 by tau 1. Drop it here, this will be Ca1. Draw another straight line with a slope minus of 1 by tau 2. Drop it here, you will get Ca2. Draw it for tau 3 and you will get Ca3. So, this is called Jones method, right, and which is a method of finding the conversion of if we have connected 3 different Cstrs in series. So, next our question will be, if I have 2 Cstrs or 3 Cstrs, what should be the optimal sequence of their series connection? Like whether we will go for the smallest, then the intermediate, then the largest, or largest followed by the intermediate followed by the smallest. What actually this, what is the rule or what should be the formalism to decide about the sequence, right. So, our topic is optimum series combination of Cstrs. Optimum combination of Cstr in series. Right. Now, you see we have 1 by minus Ra versus Xa plot, and the plot is like this. Let us say my final conversion is fixed, right, and we are allowed to design 2 Cstrs such that the total volume is minimum. We are asked to determine the total volume, that is V1 plus V2 of 2 Cstrs such that V1 plus V2 be the minimum for a given XF. So, we know that here if I am using 2 Cstrs, the curve will be, or the V1 V2 proportional area will be like this, okay, and the intermediate conversion is Xa1. So, this one is V1, this area is V1 by Fa0, this is V2 by Fa0, right. So, this total area is fixed. So, if I can maximize the area of this unused region, so equivalent problem is to maximize the hatched area, because the total area is fixed, which is 1 by minus Ra f into Xf, that is the total area, right. And you see that V1 by Fa0 plus V2 by Fa0 is equal to 1 by minus Ra at Xa1 into Xa1 plus 1 by minus Ra at Xaf minus 1 by minus Ra at Xa1 bracket into Xaf minus Xa1. So, that we have to minimize. So, our problem is minimize and we have to choose Xa1, right. So, that is equivalent to the problem maximize upon fixing Xa1 this hatched area, which is basically this is, you see, 1 by minus Ra at Xa1, that is this, right, sorry, 1 by minus Ra at Xaf, this minus this minus 1 by minus Ra at Xa1. So, I think yeah, no, here we should not have this 1 by minus Ra this much into Xaf minus Xa1. So, we will be maximizing this area because into XA1, because this is equal to 1 by minus RA at XAF into XAF minus 1 by minus RA at XAF minus 1 by minus RA at XA1 into XA1. Yeah, XA1. So, this area is fixed, right, it is independent of XA1. So, there is a minus sign. So, minimizing this quantity is equivalent to maximizing this quantity. So, that is the mathematical implication of what we were trying to discuss. So, here we are trying to maximize this area, correct. Now, see equivalent geometric problem. What is that? We have an xy space and there is a curve which is a function of x, and we have a rectangle like this, right. This is x comma y. So, our problem is maximize A, which is x into y, right. So, how we can do that? So, basically here y, because this is fixed, this is fixed, this is dependent on XA1, this is dependent on XA1, and this is 1 by minus R X1. If you see this problem a bit transformed, so the problem is equivalent to maximizing the area of this rectangle whose one of the corner is touching the curve y is equal to a function of x. So, here if I set dA dx, right, so it is y plus x into dy dx, and that must be equal to 0. So, dy dx with a minus sign is y by x. What does it mean? This means the slope of the tangent, say the point is P, at P is equal to the slope of the chord, right, P, say O, Q, R. So, this two must be parallel, slope of the chord RQ, right. So, these two, they must be parallel to each other. Right. So, here the implication is the XA will be such that if I draw a tangent here and if I join the chord, these two lines must be parallel to each other. Okay. So, physically if I try to link it, what is the condition of XA1? So, we can say that this d dxa of 1 by minus RA at XA1 is equal to this location is 1 by minus RA at XAF, this location 1 by minus RA at XA1 divided by XA1. So, that is the condition we have to establish here. So, this is the final condition, right. So, if we can, or if it is a stage, there say multiple numbers of reactors, so everywhere at this tangent and this chord must be of same slope, that means they must be parallel, right. So, this condition has been tested for multiple numbers of different kinetics, and from there what is the conclusion? The conclusion is that for reactions with order greater than 1, smaller reactors should come fast, and for order less than 1, the larger should come fast. So, what is the final recommendation? For n greater than 1, the smaller reactor, that is Cstr, must come fast, and for n less than 1, the larger must come fast, right. And for n equal to 1, actually it is independent, right. It is independent whether it is larger or smaller. Why? Physically we can explain it. Minus Ra is equal to Kca, right. So, Ca naught into dxa dt is equal to Kca naught into 1 minus Xa. So, it is independent of concentration. So, for first order, it is equal to K into 1 minus Xa, right. So, for n equal to 1, any sequence will work, right, because it is independent, the kinetics is independent of concentration. So, that is the idea. For n greater than 1, you should use the smaller reactor. That means you are keeping the concentration as large as possible, right, because here we have the monotonicity between this 1 by minus Ra and Xa, that is monotonically increasing, and when n is less than 1, which is monotonically decreasing, then we should use the larger reactor fast. That means we are keeping the concentration as low as possible, okay. Because you see that if I have minus Ra is equal to Kca square, then if we make the concentration high, minus Ra is high. But if it is K into Ca to the power 0.5, right, so you keep it low, Ca low, we have high minus Ra. So, that is the basic idea. So, you have to keep the concentration as large as possible. So, if it is this type of reactor, the smallest followed by intermediate, then the largest, right. Just the reverse for in case of that, the first the largest, then the intermediate, then the smallest. So, that is the idea of Cstr sequencing in series. Next, we will go for Cstr Pfr combination. Definitely in series. So, Cstr Pfr combination in combination. Okay. Say we have a smaller Cstr, then a Pfr, and then a larger Cstr. Right. So, here it is Fa0, Xa0 equal to 0, CA0 and V0. Here it is CA1, XA1, CA2, XA2, and finally CA3, XA3. This is V1, this is V2, this is V3. Right. We'll try to interpret the graph. Let's say n is greater than 1. So 1 by minus RA versus XA will be something like this. So first it is the small Cstr, next it is the volume of PFR, and finally it is the larger Cstr. So this is XA1, this is XA2, this is XA3, and this is 0. So this area equal to V1 by FA0. The area under the curve, because it is PFR, will be the V2 by FA0. And again this area will be V3 by FA0. Now how we can solve for the best possible arrangement? Because alternatively we can have the larger fast, then PFR, then this. Okay. So combination wise it is 3C1. So how many possible combinations? 1, 2, 3, then 2. So 3C1, 6 possible combination will result, right? So yeah, no, 3C1, and also the rest will be permuted. So 6 possible combination will result. So we have to go for, so calculate the volume, total volume, that is V1 plus V2 plus V3 for all 6 possible combinations, and from there for a given XA3, right, or calculate the, not the total volume, calculate the final conversion for all possible 6 combination, knowing V1, V2 and V3. Next, you determine the optimum combination. Right. Now what is the recommendation for all these elaborate algebraic tasks? For different order of the reaction, say if n is greater than 0, connect the reactors in series. There will be no parallel combination, right? For positive ordered reactors or reaction, if n is greater than 1, keep the concentration as high as possible. So from here the optimum combination B, definitely we know that there is no axial mixing in the PFR, so in the PFR the concentration will be highest. So the PFR, then small Cstr, then larger Cstr, right? And B, if n equal greater than or n less than 1, we must connect the reactors to keep the concentration as low as possible. That is, larger Cstr, then small Cstr, then Pfr. Right, that's a final recommendation. You must remember this because it's not possible to solve for all the different possible combinations. So you must remember the final recommendation. Okay. Now, for reactions where the rate concentration curve passes through a maxima or minima, the arrangement of unit depends on the actual shape of the curve. The conversion level desired and unit available. No simple rule can be suggested. And whenever maybe the kinetics and the reactor system, an examination of 1 by minus RA versus CA curve is good way to find the best arrangement of units. So just like this was a gate problem as far as I remember. So minus RA versus CA. So our desired concentration final conversion is here. So what will be the best possible combination? See, 1 by minus RA versus XA. This is XA, sorry, not CA. So there is a maxima, minima, maxima. So the curve will be, this maxima will be this, the minima will be this, and a maxima will be this, and minima, right. So if this is XA1, this is XA2, this is XA3, we have here XA1, here XA2, here XA3, and finally this is XAF. So definitely for the first it will be Cstr, right. For the second it will be Pfr. For the third it will be again Cstr, and this will be again Pfr. So Cstr followed by Pfr followed by Cstr followed by Pfr. This is the optimal combination, and that's why when I've seen or when you see that there is a maxima or minima in this rate versus concentration or rate versus conversion curve, so we have to physically inspect that, because in the first segment if we attach or if I am using a Pfr, this volume will be excess. In the second, if I use a Cstr, this will be the excess volume. In the third again same as first, and in the fourth same as second. Okay. So that's all about the reactor combination. In the next session we will discuss about the recycle reactor and how to find the optimum recycle ratio, and then for the rest of the sessions we will solve problems. Thank you.